to oscillation. Oscillation is a feature of the neutrino field, and it's also a feature of the quark field. Both quarks and neutrinos change from one flavour and or colour to another, and flavour and colour are analogies used by scientists to describe the differences between these quarks and neutrinos. So this essentially is a diagram that represents oscillation. I've used the double helix format because it seems to fit rather well with the model. If we think about spin as a feature of these particles, including electrons, and presumably also the muon and tau, then you can see that this spin effect supports supersymmetry, which is now dead, pretty much. And it also supports superposition, which is not dead at all, and is still very much alive and kicking, and a feature of exploration in the physics world. Oscillation in itself is simply changing from one form to another. This is an approximation of the standard model, and I say approximation because it is what you'll find on diagrams that represent the standard model, but it's an approximation because I've drawn it. Up here you've got the quarks, the up and down, strange, charmed, truth and beauty, also known as top and bottom these days, because truth and beauty were not deemed to be really suitable to describe quarks for some reason or another, but we'll look at that later. These are the leptons, and the electron is here. There's the electron. The muon is this kind of reversed U, and the tau, this beautifully calligraphed T. These are the neutrinos that correspond to these particles in some way, for some reason. This is the electron neutrino, the muon neutrino, and the tau neutrino. Of these, the muon and electron neutrinos are quite easy to detect with the hugely expensive collaborative experiments that have gone on around the world, including, of course, CERN, Fermilab, the LHC, and others.
Plenty of them.
These are the bosons. Now, bosons are not actually particles. Bosons are carriers of force. So they're also known as virtual particles because they cannot be said to have any mass. There's the gluon, which sticks the quarks together essentially and operates on a strong force. This is the photon, this calligraphed Y, and the W and Z bosons, catalysts for other behaviours between particles in their existence. We don't know at the moment whether they even fit in with oscillation, and whether they do or not is not being explored at all, so we'll leave those out of the equation for now. But this one we can't, because this is the Higgs boson, also known, unfortunately or fortunately, as the God particle. The Higgs boson is alone in being responsible for scale. It's said that when a particle comes into existence, in reality, it only comes into existence by interaction with the Higgs field. So without the Higgs boson, without the Higgs field, there is no 3D construct that we could possibly comprehend or be part of. So this is an important particle in our considerations of oscillation. The data won't show how oscillation really happens because it can't be detected in progress. Nobody knows why it happens, and nobody actually knows the answer to the inverted mass hierarchy problem, which says that the neutrinos, which are lighter and heavier than each other, which I've demonstrated here, I'll come to in a minute, they can be said to be lighter or heavier, but nobody actually knows which. As you can see so far, there are quite a lot of complications in the subject of oscillation. These are demonstrations in graphic form of the varying weights of neutrinos, so that you can see how much change takes place in the course of an oscillation for a neutrino, and also correspondingly for a quark, because the quarks are the lightest, the strange and charm come in the middle, and the truth and beauty top and bottom quarks are the heaviest. Now, this is not assuming inverted mass hierarchy within the quark field. Inverted mass hierarchy is only considered at the present moment in time in the neutrino field. So let's go back to the neutrinos. This is the little electron neutrino. And the muon neutrino is a bit bigger, but, relatively speaking, not that much bigger. The tau neutrino, on the other hand, is ginormous, humongous. It's unfathomably bigger, but it's also short-lived. And the fact that it's short-lived makes it very, very difficult to detect in neutrino experiments. The fact that it's very difficult to detect in neutrino experiments means that you can't actually see it. It's invisible. And that factor alone may well contribute to the problem with inverted mass hierarchy, because the question is this particle humongously bigger than the electron neutrino? Or is it correspondingly
humongously smaller
than the electron neutrino, which would make the electron neutrino in relativity terms huge by comparison? Now, scientists do not know where this falls, whether this balance is struck somehow, whether it exists in superposition, or whether it's some kind of problem with the way we're looking at the data. One of the gaps in understanding also that applies to neutrinos is whether they are Dirac or Majorana particles. Now, a Dirac fermion is essentially one that can be constrained to the classical physics format. But a Majorana particle is one that is its own antiparticle. So within itself, it shares the identity of particle and antiparticle at the same time. Whether or not neutrinos fall into that category is, as I say, unknown, but it's still under investigation. And again, we haven't really considered the others too much, because how do we fix a parameter on something that we cannot identify? A scientist apparently was saying it's like standing on the top of the mountain and not being able to reach the moon, so deducing from that the moon is more than 8 feet away from the mountain. There is really no correlation relativity concept that exists at the present time to explain either oscillation or inverted mass hierarchy. So both of these beg questions of the quantum field, and most importantly, the role of the bosons in being able to piece together a construct. Now, metaphysics, if we extrapolate the meta context to this word, as we would say meta language, for instance. A meta language is one that incorporates furtherance of existing language terms. Meta means greater than. So metaphysics is not woo and pseudoscience. It's what is beyond the parameters of current physics understanding. And therefore, it's essential to take it into consideration when trying to establish parameters that fit with the reality that we perceive. Oscillation is a factor that obviously falls into this category, and its exploration is going to go a long way, I believe, into understanding how change actually happens in the reality that we exist within. Once we know more about that, we're going to understand better how to adopt the properties of particle oscillation. We are made of these particles. We are made of quarks, and neutrinos fly through us all the time. So our understanding of how these particles operate is obviously going to make some kind of fundamental contribution to the way we understand and manage our personal worlds. This is part of what will be explored in Series 3, and I very much hope you'll join me for that. Please subscribe to the channel and have a look at the other quantumology videos lurking there in the vaults. I look forward very much to seeing you again soon, when we can go even deeper into what is promised in these amazing fields of quantum landscape. So thank you very much. Take care. Love you loads. See you later. Bye.